Okay, so let's start. Thank you all for coming. I need to explain a couple of things before I get started. One is why is this video camera here? Because HRI has sent a request that they want to share the same course to their students over there. So the course will be recorded and uploaded to them, and they will attend the course over there. Okay, actually there are many more students attending there than here. So I think we should honor this request. Are you people in the process of switching this on, or is it on?
Yeah, it's on.
Yeah. It's already on?
It's already on.
Okay. Now, there will be one limitation because of this thing, which is that to get a proper resolution, where the writing is readable, we have to restrict to this much of the board. This will be a bit inconvenient for you, okay. But we just have to do it and then see how it goes. Okay? Now, with that, let me start and let me tell you what will be done today, and then how we proceed. Of course, we will come up as we go along. What I want to do today is to give you giving you a 2-lecture review of the standard model. And I think it's extremely important, because if you are confused in the slightest bit about the basics of the standard model, then we don't have much chance with the MSSM. Okay. And secondly, as you know, with supersymmetry, fermions are of paramount importance. And so, whether we are using 4-component or 2-component or Weyl or Majorana and all that stuff needs to be sorted out, dotted, undotted, raised, lower, everything needs to be sorted out now. But let me ask you, how many of you feel confident that you understand what this dotted, undotted and Weyl, Majorana and everything is all about? How many people feel reasonably confident? Let's say greater than 60% confidence level. Good. Good, I'm glad at least some people are. But I think it's also clear that I need to do this. And also I need to introduce my convention. So I'll spend about 10-15 minutes doing all that, and then I will start on the standard model. Okay. So of course, the very first thing, the metric is this, which I think is the opposite of Weissenberger, unfortunately. All other conventions are pretty much the same as Weissenberger, as well as Dries, Gottwole and Roy. In fact, Dries, Gottwole, Roy is the book that I'll be trying to stick to as far as conventions are concerned. Okay, and they have taken most of their conventions from Weissenberger. Okay. So, since this is going to be about field theory and mostly about classical Lagrangians, let's get our conventions straight. So, let's write a few free Lagrangians, just so that we know what we're doing. So, for a real scalar, we have a half del mu phi minus a half, so like phi square. For a complex scalar, we have the coefficient 1 del mu phi star del mu phi minus m square phi star phi. These are pretty standard in the literature. When it comes to gauge fields, for an abelian gauge field A mu, we first define f mu nu. In the literature, there is rarely any ambiguity over this choice. And then the Lagrangian is minus a quarter f mu nu. Okay, so these are just the kinetic terms. So that we have from this, you can read back and answer your own questions, what are my conventions. Okay, if I tell you these are my kinetic terms, in a way you know my conventions. For example, this one unambiguously fixes the signature of the metric dimension. Non-abelian is a harder story, but we'll take the pedestrian approach that non-abelian is just a bunch of individual gauge fields with an extra index tagged on to them. So it's A mu A, where small a goes from 1 to dimension of a group, which will be the non-abelian gauge group. Then we'll define f mu nu A to be this plus an extra term which in my conventions is minus G F A B C A mu B A mu C. Here there is an obvious choice of sign, minus or plus, and it's completely trivial. It's just a convention because you can always change G to minus G. However, this sign is coupled with the sign of a covariant derivative. The covariant derivative will act on a, let's say, a scalar, but it doesn't really matter, could be a fermion, which would be in the representation whose index is I, where I goes from 1 up to dimension of the representation of the gauge group. And this is d mu phi I, and now there is a sign and it's correlated. It's plus Ig A mu A T A Ij phi J, where TA are generators in some representation, and they satisfy as matrices with indices Ij. They satisfy that the commutator of TA with TB is I F A B C T C. Okay. Now, as we haven't spoken about fermions at all, but if there were no fermions, that completes my review of conventions. Okay. But if anybody has any doubts about what's the convention for anything that I'm likely to use, they could ask now. Otherwise, I will get rid of all this and we will go on to fermions, which need a little bit of a chapter unto themselves. Okay, just another 5 or 10 minutes. Okay, is this all clear and is this all familiar? Now with fermions, the first source of anguish is whether we are using 4-component or 2-component notation. Since this is a course allegedly for string theorists, of which I can only see 1, 2, I think this is not a triangle string theory, 3, string theorists are not awake usually, 4, 5, pretty good. Okay. The one for whom we kept it at this time hasn't woken up, I notice. He's not around yet. Yeah.
He's around.
He is around.
He's right.
Well, now it's on videotape that good. So the anguish that this thing causes is because of the following. 2-component spinor notation is an option only in 4 space-time dimensions. In any other space-time dimensions, there is no analogous option. Okay. The 4-component one more or less continues to all space-time dimensions, but it also undergoes modifications. Its properties change according to space-time dimension. Okay. Supersymmetry and also physics, weak interactions in general, like 2-component spinors in 4 dimensions because the 2 components exhibit the chirality, the left-handedness or right-handedness. So supersymmetry likes chirality in some ways that we'll see, and of course weak interactions like chirality because they are biased between left-handed and right-handed objects. Okay. So 2-component is sort of better. And for example, some of the authors of Breeze, Goodwole and Roy assured me that this rival book by Weyl and Tata has made the disastrous choice of 4-component spinor notation, which should not stop you buying the book. But that could be a disaster. It's not disastrous, but it could make life difficult. Good. So what is the reason in 4 dimensions why this is an option? It's because the Lorentz group SO3, 1 is in a certain sense the direct product of SU2. I'm going to write cross SU2 dot. Okay, why dot? It's not my fault. It's just the same dot that's associated with dotted spinor notation. If you haven't seen that before, you're going to see it now. So let's see how this works. I'm not going to do it in detail, but use things that you hopefully know. Ji are 3 rotations. Physically just 3 rotations in the 3-dimensional space part of SO3, 1, and Ki are 3 boosts. Okay, and there's a certain algebra which together they obey, which is the algebra of SO3, 1, in which rotation commuted with rotation is a rotation, boost commuted with boost is also a rotation, and boost commuted with rotation is a boost. Okay, it's a standard thing that you can always work out for yourself. Just think about boosts and rotations, commute them, and you will come to that conclusion. You can also work out very precisely what the algebra of these 6 objects is. These I goes from 1 to 3. Now the coincidence which makes this equal to that is that if I define J, curly Ji to be Ji plus I Ki, and curly Ji dot to be Ji minus I Ki, then curly Ji and curly Ji dot separately satisfy SU2. And you should check this if you've never done it before. Okay? So they separately satisfy SU2 commutation relations, and also they commute with each other. So for any index Ji and Jj dot, this commutator is 0. Okay? What is involved in checking this is just plug in this thing and use the known commutation relations of J and K from the Lorentz algebra. Okay, so there you have it. These are the two decoupled SU2s. However, they are not quite decoupled, because as soon as you complex conjugate something, it goes from one of them to the other, because J and K are Hermitian, and therefore, although these are formally SU2 generators, under complex conjugation they really go to the other SU2. Okay, so one rule that we've learned right away is that complex conjugation interchanges dotted and undotted.
If we were in SO4, the I's would have been absent.
That's exactly right, thank you. So if we were in SO4, the Euclidean group in 4 dimensions, then the I's would have been absent, and SO4 really is SU2 cross SU2, but now if I complex conjugate something, then it stays in that SU2. Okay. Very good. Okay. Now, the spinors, what we call spinors, which will be spinors of. Spinors, by the way, in case you didn't know, is a concept that exists only in orthogonal groups. Okay, so since this group is an orthogonal group, I can say spinor of that. Okay, but it must descend to some representation of this, and what it turns out that they are doublets of either SU2 or SU2 dot. Okay. By the way, at this stage, I meant to say this earlier. The best review that I know of, or the most clear and transparent review of this whole business of dotted undotted, is in lectures of Devashish Ghoshal, which you can find in this volume, which was reprinted from SERC schools in high energy physics. Okay, it's a course that he gave on N equals 1 supersymmetry, and if you really want, I could quotes. Planned. If you really want, I could perhaps ask him to send a soft copy. People want, or people can ask him directly, or they can wait till Monday. Okay, good. So for SU2, the spinors are called psi. Well, it doesn't matter what they are called, but they have an index A. A goes from 1 to 2, and under SU2, psi A goes to a unitary 2 by 2 matrix UAB psi D. Okay. Under SU2 dot, they'll be called chi A dot. A dot takes the values 1 dot and 2 dot, and chi A dot goes to U A dot B dot chi B dot. Okay, I think it's as clear as it can be. This is a unitary 2 by 2 matrix in SU2 dot, and this is the similar matrix in SU2. Good. Okay. Now the key point is that if I take psi A and dagger it, it's a 2-component object, so the fact that dagger makes it from this way to that way is hardly important. Some people put in transpose signs, but it's a waste of notation. If you just dagger it, which is the same as starring it, complex conjugating it, then it turns into an object psi dagger whose index is now A dot. Okay? So if psi had an index A, then psi dagger has an index A dot and vice versa. Here for some reason, Riesgotole and Roy have introduced a bar, but their bar, as far as I could make out, is the dagger. There's no difference, so there's no need for two notations. But I think in their notation, it's a bar. Okay, and so this is clear. Good. So that sort of sets up what the SU2 cross SU2 structure is. Now, for the purpose of writing physical quantities like Lagrangians, we need to make invariants under SU2. And here we finally begin to see the significance of another very arcane operation besides dotting and undotting. The other arcane operation is called raising and lowering of indices. Okay? And the reason for that is that given psi A, we would like to make a bilinear invariant, but psi transforms only under the first SU2. Okay? So we are only allowed to use U. Okay? Now psi times psi, some bilinear, has to be invariant and it's going to have two U's. It's not going to have a U and a U dagger. U and U dagger, of course, make one because it's unitary. It's going to have a U and a U. So our problem is to find some linear combination of two psis which is invariant after we transform each of them by a U only, without involving any U star or U dagger. That's possible. Of course, I'm sure there's more mathematically pretty ways to say this, but this is a very practical hands-on reasoning. And so what we do is, we propose that there is some numerical tensor epsilon AB, two-component tensor, second-rank tensor, such that, I'm just choosing my things carefully, epsilon BA contracted with psi A, chi B is invariant under SU2. Of course, it's invariant under SU2 dot because nothing here transforms under SU2 dot. But we'd like this to be invariant under SU2, and that should determine epsilon. Okay. So, of course, under SU2, what does this go to? It goes to epsilon BA, which is just a constant, some numerical tensor which we have to determine. And then this goes to UAC psi C, and this goes to UBD psi D. And the invariance condition is that this same thing should be epsilon BC psi C chi D. Okay, so that's the condition we require. And the nice thing is that this has a solution. So this equation implies that epsilon BA UAC UBD is equal to epsilon BC. Now a simple way to think about how this is solved is to ask, so I can just, so first of all, there's a simple solution to this. Let me give you the solution, then I'll just tell you how you would have got it. So the solution is that epsilon AB is equal to 0, 1, minus 1, 0. Anti-symmetric for one thing, and it's 0, 1, minus 1, 0, which is why we are given it the name epsilon. I emphasize it comes about by solving this. Now the reason why this happens is something that you can check with Pauli matrices. You see there are three Pauli matrices, sigma 1, 2 and 3. And together they generate all SU2 matrices just by exponentiating them. The middle one, sigma 2, is imaginary, the other two are real. Okay? So if I conjugate by sigma 2, then the real ones will flip sign while the imaginary one is sigma 2 itself, so it doesn't flip sign because it commutes with itself. Okay? And then if I add another minus sign, then it basically amounts to complex conjugation. Okay? In other words, I take sigma 1, sigma 2, sigma 3. If I conjugate by sigma 2, conjugate means multiply on both sides by this and its inverse is itself. Then I get minus sigma 1, sigma 2, sigma 3. Then I change all the signs. Sorry, minus sigma 1, sigma 2, minus sigma 3. And I get minus sigma 1, sigma 1 minus sigma 2, sigma 3. But sigma 2 being imaginary, this is sigma 2 star, and these being real, this is sigma 1 star and sigma 3 star. Okay? So basically, after a minus sign, the process of conjugating by sigma 2 just complex conjugates all the Pauli matrices. Okay? In fact, we can absorb the minus sign if we conjugate by I sigma 2. Okay? So I sigma 2 is the thing which complex conjugates all Pauli matrices. Well, if we complex conjugate this U, then it becomes U dagger and then U dagger U is 1. Okay, the whole problem was how to make U square into 1. It's done by complex conjugating this. And I sigma 2 is that. So that's the reason why this works. Okay? Okay.
You could see there's a formula for the determinant.
Yes. That's all, yeah, okay. Okay, thank you. I think that may be, that's perhaps an even, that's even less complicated. That's a much simpler way of seeing it. So this is the formula for the determinant. So actually, if I probably contract with epsilon on the left side, then it's really a formula for the determinant. And determinant of the unitary matrices is 1. That's the S part of SU2. So that's what does happen. That's actually very. In fact, you contract with epsilon on both sides. Then you put the epsilon with epsilon will give you a 2, so you put a half, so you have half epsilon, epsilon this, and that's actually the determinant being equal to 1. Much better. Okay. Good. Good. So what we've learned is that this thing is invariant. And this motivates us to write the invariant epsilon BA psi A chi B as psi B chi B, where by definition epsilon BA psi A is psi B. Okay. You can also define epsilon with lower indices, and those are minus of the epsilon with the upper index. And that allows us to invert this relation with the same sign. Namely, if I did epsilon AB on this, I get psi. Okay. This is just a definition. Okay. What this definition does is allow us to write this as this. Okay. And this is written sometimes just psi chi, and in a course on supersymmetry, we'll be seeing this many times. Just the product of two spinors without any bar, complex conjugation, indices, nothing. Okay, you have to remember that this is this combination, and you even have to remember, unfortunately, that in this case the first index is up and the second one is down, which is what I think Devashish calls the north-west to southeast convention. Okay, there's the unfortunately but for good reason, with the dotted spinors it's different. With the dotted spinors, if we wrote psi dagger chi dagger, then this is defined to be psi dagger A dot chi dagger A dot. It's the second guy, which is that. We'll see actually why that's natural. Okay. One useful identity I might as well tell you at this stage is if I take psi, it's actually this is really useful, and this is probably why this is done. If I take psi chi, it's actually equal to chi psi. The reason is flipping these two, because they are going to be, these are all anti-commuting fields, that I'm sure you already know. So flipping the components will give a minus sign, but then this contraction is defined by raising with epsilon this guy, while this contraction is defined by raising this guy. Okay? If we change our minds about who we raise, then we get a minus sign. And therefore, these are actually the same. Okay? Moreover, if I take the dagger, then I get chi dagger, psi dagger, which is of course the same as psi dagger, chi dagger. Okay, all with plus signs. There are no minus signs in this set of formulae, which is a good thing. All right. Good. So that much about spinors in general. And now we can ask what are the fermions in field theory. Are there any questions on this? What I have done up to now is to show you how to go from dotted to undotted and why, because they go from one SU2 to the other, and also how to make invariants within one SU2 or the other SU2 using an epsilon symbol. And and that's what gives rise to raising and lowering of the spinor index. Okay. Now, the more familiar perhaps 4-component fermion of SO31 that is used in a lot of field theory textbooks, including Peskin and Schroeder, more or less exclusively. This thing has a decomposition in which its first 2 components are a lower undotted spinor, and its next 2 components are a upper dotted spinor. Okay. The fact that I am calling this chi dagger is a convention. I could have called this one chi a dot, but then its undotted counterpart would have had a dagger. So that's pure convention. Psi and chi are totally independent of each other, so there are 2 different 2-component spinors, one in the SU2, the other in the SU2 dot. And the fact that this one has its index up, I don't know any simple derivation of, but it's just a fact. If you go from SO31 to SU2 cross SU2 dot, that the first 2 guys have the index down, the next 2 guys have the index up. It's not very hard to see why, but I don't want to go into it now. Okay, so this is the decomposition, and in a particular basis, in the Weyl basis of SO31, which means that the gamma mu's are according to the what is given as the Weyl basis, which means that they are basically off diagonal for the gamma mu's, and gamma 5 is diagonal 1 minus 1, or sometimes minus 1 and 1, not very important. Then we can write psi as psi left and psi right. And so we naturally see that in the Weyl basis, these 2 procedures are quite equivalent, 4-component and 2-component. And the upper 2 components so are identified with a 2-component spinor of SU2, and we can call it left-handed. And the lower 2 components are identified with a dotted spinor, so from the other SU2, and we call it right-handed. So another thing we learn from this exercise is that undotted and dotted is the same thing as left-handed and right-handed. Okay. Good. Now with enough of this, one can start to write down the action, and the free action will be I psi bar gamma mu del mu psi minus m psi bar psi in general for the 4-component guy, and it's a very simple exercise to translate all of this into 2-component. I would urge you to do this. Okay, I'll write down for you the answer, but first I'll write down for you psi we have taken to be this. So the question is, what is psi bar? So it should naturally be written as a horizontal 4-component object, and a little exercise will show you that psi bar is, I can't seem to spot it, yeah, chi upper A and psi lower A dot dagger. So this is a nice symmetry. What happens in barring is, first of all, in barring, the left and right-handed components get interchanged. Okay, so right-handed fermion becomes left-handed and vice versa. And then of course it also involves daggering, so obviously the dagger should disappear and this index should come out undotted here and dotted here. Okay, so that's psi bar. And then we find that this L can be written as I chi sigma mu del mu chi dagger plus I psi dagger sigma bar mu del mu psi minus m chi psi minus m psi dagger, where sigma mu is 1 and the 3 Pauli matrices, while sigma bar mu is 1 and minus the 3 Pauli matrices. Now, this is already the start of expressions where some tricky things are buried in the indices. For example, this, I haven't made it completely clear in writing this, whether these indices are raised or lowered. I'm not sure if you can actually deduce it from what I've said up to now. So I need to tell you what I mean by these two contractions. So the first one, so I chi sigma mu del mu chi dagger means I, then chi has its indices up, sigma mu has an A and a B dot index. It might not actually matter, probably, sorry, this is also. Okay, so sigma mu is naturally defined with two lower indices, one undotted, one dotted, so that it's able to contract between a chi and a chi dagger dotted. The other term, I psi dagger sigma bar mu del mu psi is I psi dagger. Now we put the index down. A dot sigma bar mu A dot B del mu psi B. So we see that sigma mu has naturally a first dotted and second undotted index, while sigma bar has first and, sorry, whatever I said, you see what this is, and then this is the other one. Okay. Good. So that sets up the state for what is called a Dirac fermion. And just so that you have the physical concepts clear, the Dirac fermion encodes the states of a particle of spinor, let's say a left-handed particle, a left-handed antiparticle, a right-handed particle, and a right-handed antiparticle. Okay, that's one way to say it. Okay. Now, one thing I hope you all know is that CPT conjugation in 4 space-time dimensions, though not in all space-time dimensions, takes a left-handed to a right-handed particle. So anything that I say for a left-handed particle is also true for a right-handed antiparticle. Okay. That's something to keep in mind. We will perhaps encounter it later. Okay. Now let's do another thing which becomes very important as we go along, which is to consider constraining this Dirac fermion to have less degrees of freedom, which can be done in 2 possible ways, which are actually equivalent. So one is the possible constraint which says that chi is 0. That is, we have a Dirac fermion, but there is no chi. Chi is because we can choose psi and chi arbitrarily, so just choose this one to be 0. Okay, and that one we keep. Okay, so this is called a Weyl fermion. And we see that physically this corresponds to having a left-handed fermion, okay, but no right-handed fermion. If there's a left-handed fermion, there's bound to be a right-handed anti-fermion that you can't get away from. Okay, but in the left-handed sector, we say that there's in the fermions, in the particles only, as distinguished from the antiparticles, there's only left-handed and not right-handed. That's a Weyl fermion. Okay. To get the Weyl fermion action out of what I've done here is extremely simple. You just set chi equals 0. This is the end result, this Lagrangian here. Set chi equals 0 in this Lagrangian, and you find I chi sigma mu del mu chi dagger. Sorry, psi is the one I'm keeping. So it's actually I psi dagger sigma bar mu del mu psi. And that's it. All other terms have gone to 0. Okay. In particular, the mass terms have gone to 0, which teaches us that a Weyl fermion can't have a mass term. Okay. We could have taught that to ourselves from inspection of this, because this is associated with the left-handed and right-handed parts of the original spinor, and we see that the mass term couples the two, while the kinetic term only propagates one or the other. Okay, so obviously if one of the handednesses is missing, then there can't be a mass term.
Sorry, so is the expression chi identically 0?
No, it's not.
Why couldn't we add that to the Lagrangian?
Yeah. Good question. Actually, so the point is that we could actually, and chi is not real, therefore there will have to be a chi dagger, and that will turn out to be the Majorana fermion, which has two components, but the lower one is the dagger of the upper one. Okay. Now we can also do that for this, because the Majorana and the Weyl fermion are actually equivalent. It's only which coupling. Let me finish Majorana, and then I think your question will have a natural answer. Okay. So this is one possible constraint, that chi is 0. There is a second equally natural constraint which we can put in this spinor, and that is that chi is the same as psi. In other words, the thing whose dagger we put over here, that chi is chosen to be the same as the psi which was up there. Okay, that's an alternate constraint, and this is called Majorana. So let's rerun this side of the board for the Majorana case now. Now the Majorana case, for quite good reasons, has a factor of half in the Lagrangian compared with the other cases. That's because it's more like the analog of a real scalar compared to a complex scalar. So what I'll just do is run through this by putting a 2 here. Okay, that means every formula here gets a 2. Every term gets a 2. But also I need to say that chi is the same as psi. So I'll just rewrite this as chi. So this is for Majorana. Now this can be rewritten nicely. So here's an exercise. By taking this, you see here there's chi on the left, here there's chi on the right. If you take this chi to the left and that chi dagger on the right, and also take care of raising and lowering indices properly, this sigma bar will turn back into a sigma, and the first term, the kinetic term, will turn out to be I by 2 chi sigma mu del mu double-sided on chi dagger, which means this term with del mu on that minus the same term with the del mu acting on the left. Okay, and then the other terms stay, minus m by 2 chi minus m by 2 chi dagger chi. Okay, so we see that there is nothing unnatural about having a mass term for a Majorana fermion. Okay. Now the relation between a Majorana and a Dirac and a Weyl fermion is that if we take the Dirac fermion and constrain it to be Weyl, set chi equals 0, we can also take its charge conjugate, which will have 0 here and psi dagger here. Then we add them and we get a Majorana fermion. Okay. So what the key to this is that in the Majorana fermion, I am no longer allowed to say that I have a left particle and no right particle. In fact, the Majorana fermion will be its own antiparticle. So the whole notion of antiparticle and particle goes out the window. The distinction between particle and antiparticle goes out the window. Okay. Let me see if people here are willing to help me out. Why do we really need the distinction between a particle and an antiparticle? In practical, not Shiraz, anybody else. In practical life, what is the key distinction? Charge. Thank you. Okay. So when it comes to neutral particles, there is not a very sensible distinction. For example, the photon is neutral, and in fact there isn't, and nobody's ever heard of an anti-photon because it's the same thing. Okay, and we'll see in fact that supersymmetry as a consequence will tell us that the super partner of the photon, the photino, will be naturally a Majorana particle. Okay. However, if we are going to assign charge, then we need the particle to be distinct from its antiparticle, and then Weyl is the more natural notation. Okay, and there's one, of course, there's one weird exception, which is the neutrino, which although it doesn't have charge, it has an SU2 representation. Okay, so you still can distinguish neutrinos from antineutrinos. They have hypercharge, although not charged. And there we'll find what more or less what Shiraz was suggesting, which is we can take the Weyl object and put a Majorana type mass term. That's called a Majorana mass for the neutrino. Okay, so I realize that this is not the simplest of things, but this is actually a somewhat complicated issue, and I see people looking puzzled. So I'll pause if there are any questions. Okay. maybe what I can usefully repeat is that this is the most general fermion, and we wrote the Lagrangian in 4-component notation without the factor of 2. If we make the constraint that this is 0, then we can of course reduce the Lagrangian to that case and we find the mass disappears. If we make the constraint that this is equal to the dagger of that, then we get this form where the mass doesn't disappear, the two kinetic terms combine, and there are still two mass terms because one is complex conjugate of the other but doesn't disappear, and some factors of half come into this term. And I think the best way to illuminate all this will be to see where we are going to apply these ideas. Because we will, in this course at least, we will be applying them to real particles that can be measured and observed, and for which we know all their properties. And yes.
This Weyl fermion that we had, it can either represent, it can represent both a left-handed fermion and a right-handed antifermion.
It does always, because its complex conjugate is the right-handed antifermion. Because these things are intrinsically complex, it necessarily does. There is no option on your part.
How do you distinguish between the two, whether it's representing this or that? Or
it's a bit like asking for the scalar field where life is less complicated. Phi represents a complex scalar field, so it's a charged particle, and phi star represents the complex conjugate particle. CPT guarantees that there is nothing a particle can do which is different from what its antiparticle can do. If you CPT conjugate them, see the whole point of parity violation, it says that left and right-handed particles can behave differently, but left particles and right antiparticles have to behave the same because they are just complex conjugates of each other.
So experimentally you cannot distinguish.
Experimentally you can distinguish it by fixing one of the things to be a particle. You cannot make an overall distinction that these are particles, these are antiparticles, but if one thing is fixed to be a particle, then relative to that there is a natural definition of all the other things. Let's come to a theory. We haven't come to a theory yet, but we are going to in fact in this. So when we come to the theory, then you can ask the same questions. Okay, one very minor comment is that Rees, Gottole and Roy define, in my view, unnecessarily a del mu inside a box, which is half times the double-sided del mu that I have defined. Okay, and with that, we finally come to the end of our notation business. I didn't write the minimal coupling of a fermion to a gauge field, but there's no difference because the fermions, spinor indices don't participate in minimal coupling. When you write a covariant derivative capital D mu, whatever I wrote for scalar fields with an index capital I going from 1 to dim R will be the same for fermions, and it won't matter whether they are chi's, whether they are undotted, dotted, 4-component, 2-component, makes absolutely no difference. Okay? So minimal couplings of fermions to gauge fields, again, I've already defined. Good. So now we come to, so that's, I hope it wasn't unnecessarily long, but I think important review of notation. And now we come to the standard model. Good. Now there are many ways to introduce the standard model, and depressingly for me, most textbooks take the attitude that they just take the whole standard model and hit you on the head with it, which I find very painful. And I'm going to do it a little differently, and I'm going to try and make a little logical sense. It has its arbitrariness, but it's only in 2 or 3 places, and I'm going to try and do it in the way that I understand it. So from my point of view, the thing to introduce first is the gauge group. And there's excellent motivation for the gauge group, which is SU3 cross SU2 cross U1. Some people like to put an L here, but there's no such thing as SU2L. There's only a group called SU2. So I'm going to call it SU3 cross SU2 cross U1. There are firm-taken representations which are correlated between the SU2 charge and the Lorentz transformation property. Those are called L. They will come later. Okay. Now, so this is the gauge group, and we'll give names to all the gauge fields. SU3 has dimension 8. The gauge fields are going to be called G, mu, A goes from 1 to 8, for SU, A goes from 1 to 8. For SU2, the gauge fields are going to be called W, mu, A goes from 1 to 3. And for U1, the gauge field is going to be B mu, and it's abelian. Okay. Now at this stage, there is no point giving names to these particles because we don't yet know what the physical spectrum will be, and because a Higgs mechanism is going to take place on this sector, it will be a little different from what it appears in the beginning. However, because these are gauge groups, we need to give the names to the gauge coupling constants. And I'll write them in the same column here. The coupling constant of SU3 will be called G sub 3, 3 for SU3. The coupling constant of SU2 will be called G sub 2 for SU2. And the coupling constant of U1 will be called Gy, where Y is called hypercharge, and that's actually the name given to this U1. Okay. Now the logical next step is to introduce the various matter fields. As we know, the standard model only has fields of spin 1, half and 0. I've already told you all the fields of spin 1, so I only have to tell you the fields of spin half and 0. Okay. Now here's a case where it's actually easier to write down the principles in words than in equations. It's clearer, and I'm going to write down the principles in words. Okay. Principle 1 is all quarks are in triplet of SU3. So I'm going to write down two types of fermion fields, quarks and leptons. All leptons are in singlets of SU3. So this is principle 1. Principle number 2, okay, is that all left-handed quarks and leptons are doublets of SU2. All right-handed same things, quarks and leptons are singlets of SU2. Okay. Now in line 1, I've told you the representation of SU3 under which all the matter particles, quarks and leptons transform. In line 2, I've told you the representation of SU2 under which all the quarks and leptons transform. Okay, this is almost enough information to write down the basic structure of the model. The third one, I should tell you proceeding in logical sequence. So I've told you the behavior of these fields under SU3 and SU2, so I should tell you under U1. Okay, and here comes the interesting thing. U1 charges are to be fixed by experiment. They are not some simple things like saying doublet or saying triplet. Okay, first of all, abelian group in a way is more complicated because you can really choose any charge you like. Okay, you can just choose any number. So there's no principle which guides us to the number, but we'll find that experiment will fix the U1 charges for us. However, not exactly in the way we might think naively, because this U1 is not the U1 of electromagnetism, in which case the electric charge would be these U1 charges. Instead, these are hypercharges, and so we'll proceed leaving these free until the very end when we can see how to fix them. However, there's one thing you should note, of course, that the U1 charge of any of these must be the same for all members of a doublet or triplet. That is, if something is in a triplet of SU2 or a triplet of SU3 or a doublet of SU2, then all of them must have the same hypercharge. Okay, we can't say that one of the triplet has one hypercharge and the other doesn't, because then hypercharge will fail to commute with that symmetry and will break one or other of those symmetries. Okay, is that clear? Okay, so you can now write down without any further ado the table I am just going to write down for you. You can reproduce it yourself from these three principles, and I think these are all easy to remember. Maybe before we write, let's see why they are, what physically motivates them. Okay, the fact that protons and neutrons have three quarks in them, age-old discovery. Statistics requires you to have three species of quark in order for the thing to not violate the exclusion principle. That tells you that there are three types or three colors of quark. Later development was that those colors are really gauged, and there's an SU3 gauge group, there's asymptotic freedom and all the rest of that story. Leptons don't participate in strong interactions at all. So if there's a strong interaction gauge group, the leptons shouldn't know anything about it, so they must be singlets, which is the only possibility for them to be neutral under that. Okay. The second requirement comes from parity violation, which is maximal or V minus A type, which says that the distinction between left and right-handed fermions is as great as possible, and in fact so much so that this SU2, which is responsible for the weak interaction, really doesn't couple to the right-handed fermions. It only couples to the left-handed fermions. Okay. And the third is an obvious statement. Okay. So with that, we write the following. So here is the up and down quark, left-handed. And each of them has a hidden index, which is the triplet index. And what you will see is that in this discussion, the triplet index can always be suppressed because nothing subtle happens to it in the dynamics. I mean, something very subtle happens, which is confinement, but nothing happens that at the level of classical manipulations like this. So every statement just copies 3 times for the 3 members of a triplet. So we suppress the triplet in this. On the contrary, this is the doublet structure which I promised here. Left-handed quarks are doublets of SU2, and I have made it explicit by writing the 2 members of the doublet as U and D. I could also have written them as Q1 and Q2. They are identical up to now. Okay, they are completely indistinguishable at this stage. Okay, and their representations are given as 3 underlined, which is the triplet of SU3, 2 underlined, which is the doublet of SU2, and an unknown quantity YQL, which is the hypercharge for this doublet. Similarly, there is a lepton doublet. I am writing one generation only, by the way, and this differs from that by being the 1, 2, and YL. One more thing to remember is that in the first 2 cases, because this is SU3 and SU2, this is the dimension of the representation. So 1, the singlet representation, is like having no charge or like having no coupling. Okay. Here on the contrary, we have the value of the charge. So the analog of being a 1 under hypercharge would be to have y equals 0. Okay, so far so good. Next, we look at the right-handed up quark. This being a quark is in the 3, but being right-handed it's in the 1, and it has its own hypercharge. The right-handed down quark, likewise 3, 1, and its own hypercharge. And now you see these two don't have to be equal. They are hypercharges of right-handed quarks. Right-handed quarks are not in a doublet with each other, the U and D, because they are singlets of SU2. So they are allowed to have, and they will have, independent hypercharges. Okay. Likewise, nu E. Now this will be a singlet under SU3 because it's a lepton, singlet under SU2 because it's right-handed, and its hypercharge will be independent. Doesn't take much to guess that that's going to be 0. For a while there was no right-handed neutrino, but now we know that there are right-handed neutrinos. Some people still, in my opinion, unnecessarily insist that the standard model is the model without right-handed neutrinos. So I think what standard also evolves. So okay, 1, and then this has its own hypercharge. Okay, so that's the whole story, and this is a complete listing of 1 generation of quarks and leptons following this principle. introduce more generations until the next lecture, because they really come in when we start to discuss the mass matrix, which I am not going to introduce right away. So let's see how far we can get with this one generation. But I should say one generation. You could take this as a sort of toy standard model. Okay, now here's an exercise. Examine the CPT conjugates of all these particles. By examine, I mean think about them. Realize first of all that there must be an up antiquark and a down antiquark. Okay, and an anti-neutrino and anti-electron or positron. And that in that family, yes, in that family, it's not so much that they are right-handed. There are right-handed and left-handed of everybody, but in the antiparticles, the up antiquark and the down antiquark will, which are right-handed, are in a doublet of the weak interactions. Okay, the up antiquark and down antiquark, which are left-handed, are in singlets of SU2 because they are the antiparticles of these. Okay, so I've actually answered that exercise for you. That's really all there is to it. The antiquarks are also in the anti-triplet or 3-bar representation of SU3, which is a different representation from the 3 of SU3, but its properties are identical, of course, because it comes under complex conjugation. And finally, the Y's will all be with the minus. So that solves that exercise. But it's very important to keep in mind that whenever there are these, there are also the antiparticles, and that's so even if we don't bother specifying. Good. Okay. Now we are going to do what's usually done, ignore SU3 for a long time. Because SU3 doesn't participate in the Higgs mechanism, which we now need to talk about. So now we need to introduce. Okay. Good. Before we introduce the Higgs field, let's see how these existing things actually transform under the SU2 and U1 gauge transformations. So it will help us for the future to write it, as well as it fixes a convention which is already fixed in principle by the other conventions I've given you. So I want to know how U and D transform under an arbitrary gauge transformation in SU2 and in U1. Okay. Under the gauge transformation in SU2, I have to write down for you an SU2 matrix which pre-multiplies this doublet. It has a factor G2, which is the coupling constant of SU2. It then has 3 parameters which are called alpha 2a of x. These are, because it's a local gauge transformation, they depend on space-time. And they are called alpha 2 because they are the parameters for the SU2 part. Okay, and therefore their a goes from 1 to 3. This multiplies the generators of SU2, which I can immediately write as sigma A over 2, where sigma A are the 3 Pauli matrices. Okay. So this is the SU2 matrix that multiplies that on the left. In addition, I have to give you a phase which comes from U1, and that is written as e to the minus I Gy, the coupling constant of the hypercharged group, times a parameter, which is the hypercharged gauge parameter, times the hypercharge divided by 2. This is just a convention. Okay. And here the hypercharge in this particular formula will be that of the doublet in question, QL. Okay, this fixes conventions. I have defined hypercharge value such that this by 2 multiplies these things. I hope all these factors are very clear what they mean. Okay, this is the usual theta in abelian gauge transformations, and this is the usual set of 3 thetas in non-abelian SU2 gauge transformations. I just need to give them different names. Okay. Contrast this with the fact that UR doesn't have this at all, being a singlet under SU2. So it only has e to the minus I Gy alpha y of x, y of UR. In fact, I'm going to just keep writing y. When you see a y, you have to fill in the value for that thing. Okay, TR ER similar, new R similar, and new E and E left. So this exhibits it very bluntly for us that the doublets have this factor and this factor under gauge transformations. The right-handed singlets have only the abelian factor under gauge transformations. That's precisely the setup we made. So now time to introduce the last field of the standard model, which is the Higgs field. Now with the Higgs field, which of course hasn't yet been formed, we would have many choices because we could choose the representation arbitrarily. Unlike all these, you see, these first generation particles have all been known for ages, and there isn't any doubt about the fact that U and V fit in a doublet. They can't fit in a 5-dimensional. There is a 5-dimensional representation of SU2, but that couldn't be the one for the up and down quark because it would require other quarks. We haven't found those quarks. It doesn't fit. It doesn't make sense. Lots of things will fail. With the Higgs field, it's much less clear what will fail. So one needs to try, in principle, many options. And there are actually many options. In fact, the first option, I think, which predates Weinberg-Salam was Georgi-Glashow, in which the Higgs field was a triplet. Okay, and with the triplet Higgs, you can actually break SU2 to U1. And that seemed nice because you want a U1 at the end of everything because you want electromagnetism. But that model failed to predict weak neutral currents, which is the existence of another neutral gauge boson that's not the photon and that's massive. And such weak neutral currents were found experimentally, and it was the kind of killing, I think, it was a kind of crucial test of the Weinberg-Salam model because it predicted those. Okay, so it is just to say that it's important what you choose the Higgs field to be, and now we are going to choose it in accordance with Weinberg-Salam model to be so it's two complex scalars in a doublet of SU2. We'll also sometimes call this phi, where you have to imagine that this is the two-component field, and each of these is also complex. Okay. No charge under SU3, so it's a singlet of SU3 because we don't want the Higgs to participate in strong interactions because it would only mess them up. Okay. However, it can have a hypercharge. So therefore, the assignment of phi1, phi2 is 1 under strong interactions, 2 under this. There's no left and right handed in a scalar particle, so we can't give them different quantum numbers under SU2. And finally a y of the Higgs, which, like every other y that we've encountered so far, will leave unfixed for the moment. Okay. Now, the motivation for introducing the Higgs is the fact that with the existing particle structure, largely motivated by experiment, and the existing gauge symmetry, we have trouble writing down mass terms. In fact, the parity violation built into this model which amounts to the statement that right-handed particles are SU2 singlets, makes fermion mass terms difficult. That's the first thing we need to convince ourselves of. So why is that? Well, I said that it's very simple from whatever I introduced earlier. I had said that all the left-handed fermions are doublets and all the right-handed fermions are singlets, okay, of SU2. So how on earth am I going to make a mass term which is supposed to be a product of a left-handed and a right-handed fermion and have it be gauge invariant? Okay. So L doublet times right singlet is not gauge invariant. The mass times this times this. Okay, so that's the problem. Another problem is that the gauge fields, another problem but a slightly different kind of problem is that we also can't write mass terms for the gauge fields. Okay, And what we know about the dynamics of gauge fields is that if we don't write mass terms for non-abelian gauge fields, then they typically generate their own virtual mass by being confined. Okay, it's not really a mass, but the fact that they are confined explains why there are not massless gauge fields floating around. This is important. Mass terms is crucial because the standard model as it is that I've written predicts a whole lot of massless particles which clearly don't exist. Okay, so almost nothing in this model is allowed to be massless. The only things that are allowed to be massless are the ones compatible with the experiment, which tells us that there's only one long-range force other than gravity, and that's electromagnetism. Okay. So this is a problem. Okay, there is an exotic solution, but valid only for the neutrino, the so-called Majorana mass. But I have a feeling we are going to be discussing neutrino masses later in this course, so we'll ignore it for now. What it amounts to doing is giving a mass not between the left-handed particle and the right-handed particle, but the left-handed particle and the right-handed antiparticle, which violates particle number. Okay, not particle number, but particle number if you like. But since particle number, as he pointed out, is basically electric charge, we are allowed to violate that if we do it with neutrinos, which have no electric charge. We can't do this with any other particles. So this solution anyway wouldn't have helped us much. At best, it would have helped us with neutrinos. Okay. So we need to find out how to give masses to the other particles, and the mechanism starts by giving a mass to the Higgs field, and that's the one thing that isn't forbidden with all the field content I've written down. Okay. So this was the mass problem. For the Higgs, yes.
So let me understand the problem.
Yeah.
So because of SU3, you have to have the product of 3 and 3 power.
If it's a quark, yeah. But we could try the electron masses. We can forget about SU3.
Okay. So suppose we were doing the lepton. Why can't we have something like chi, which would then take the
Chi is a Majorana mass.
Okay, well, I see. So you're saying that that's allowed?
That's allowed, but the thing is, chi is exactly the thing which violates. So chi has two chi's. So if chi has a charge, then chi has charge twice of that. Right? So we're adding a term of charge 2 in the Lagrangian, which we can do only if 2 is multiplied by 0, which is a massless field. That's not a massless, a neutral field. That's only the neutrino in the entire spectrum of
the neutral field under the U1.
Under the final U1, which hasn't emerged yet, the electromagnetic U1.
I see. Under the SU2, we can take doublet times doublet and get a single.
The SU2 is not the problem, I think. Yeah.
Okay, so if I think in terms of the original gauge groups, then I can make something neutral under the SU2, but it's that the U1, this hypercharged thing, that's the problem.
Yeah, actually, I think you can probably, I'll think about this. I think probably you have a choice whether to count the quantum numbers before or after Higgs mechanism. Probably both should work in some sense. But the physical coupling are really, okay, so this is before Higgs, if you like.
Yeah, just in the model.
Yeah. Now, that's right. And here, it's probably U1 hypercharge which is stopping.
Okay.
And it's only the right-handed neutrino which has no U1 hypercharge.
Right. And so things charged under the SU3, anyway the 3 plus 3 has no singlet. 3 times 3 has no singlet, so that would forbid.
No, but if you are, because the mass term connects a particle, so normal mass term, okay, it's confusing, but a normal mass term is like, you can imagine it as an interaction with a left particle going in and a right particle going out, but both are particles.
Right.
Okay. However, in the Lagrangian, one of them is written as a bar because it's an out state, so it carries the opposite charge from the other one, and so the charge is conserved. Because you see, charge obviously, if I count incoming charge and outgoing charge is going to be the same in this process because it's a particle going to a particle. Okay, so this is a normal mass. A Majorana mass has a left-handed particle and a right-handed antiparticle coming out of this thing. Okay, so
the first guy is okay with SU3, the second guy has potential.
I think that the second, yeah, maybe you're right. Maybe the second guy does have a problem with SU3, you're right. SU2 we might get away with because it's tutorial, so the doublet we might be able to make some singlet out of it, but SU3,
there's no singlet in 3.
There's no singlet in 3 cross 3. I think you're right. Besides the fact that hypercharge is okay. So, okay, thanks. That's actually a nice formulation. Good. Okay. Fine. So now we come to Higgs. And with Higgs, nothing stops us writing a completely well-defined mass term in the sense that Higgs is an SU2 doublet. So I can write phi star phi type of mass term. It's SU2 invariant. It's U1 invariant. It doesn't SU3 doesn't enter anywhere. There's no prohibition on the mass term for the Higgs. Okay, but in fact, we are going to do more than write a mass term. We are going to introduce a Higgs potential, which is actually minus mu squared phi star phi plus lambda phi star phi squared, where phi star phi means phi 1 star phi 1 plus phi 2 star 2. Actually, it's probably best to call this a dagger, which will remind you that phi is the SU component of it. Okay? So this is certainly allowed. And what we are going to do, which is the famous Higgs mechanism, is to choose this to have the structure in mod phi space of a double Weyl with a local maximum near phi equals 0 and an absolute minimum at some finite distance away. Okay? And it's rotated, or it's more than that, because this is really a 4-dimensional. These are 4 different real fields, if you like. So this is a multi-dimensional field space. Okay. So now if we try to minimize this potential by saying that del V by del phi 1 is equal to del V by del phi 2, which is equal to 0, and moreover that it's not a maximum, that would be there at phi 1 and phi 2 equals 0. If we really look for a minimum, we find the minimum exists at phi 1 star phi 1 plus phi 2 star phi 2 equals lambda mu squared rather over 2 lambda. And by convention we call this v squared by 2, defining v to be square root of mu squared over lambda. So that means that to minimize this potential we have to choose a Higgs field which has this total modulus v squared by 2. But of course we can do that in lots of ways. After all, it's a two complex component object and we have one equation on it. So there are still 3 free parameters. Okay, choosing this a wave which satisfies this, there are 3 free parameters, but SU2 the group has 3 parameters. So we can use those up and bring the Higgs to any particular form we want. And the particular form we want is that phi 1 phi 2 wave is 1 by root 2, 0, v, and v is real. Okay, so what we've done is to remove this component altogether as well as the phase part of this component. Okay, but in the process, so using SU2, and perhaps worth mentioning here, though it's not a cause for formal theorists, but still worth mentioning, that SU2 being a local symmetry, what we have done is just made a gauge choice. Okay, so this wave is actually physically equivalent to all other waves, so it doesn't break any symmetry. It's not really spontaneous breaking of symmetry. It would have been if SU2 was a global symmetry, but because it's a gauge symmetry, the correct thing to say is that it realizes the gauge symmetry in the Higgs space. Okay, and we'll see that in fact there is not a Goldstone boson because this is not spontaneous breaking of symmetry. There is a Higgs boson because it's a theory in the Higgs space. Textbooks are unfortunately rather careless about this, but anyway, this distinction really won't make any difference for us. Okay, so this. Good. So that means that we have used all of SU2 to make this choice. So apparently SU2 is broken, or as I prefer to say, Higgs. And if that was true, then the three SU2 bosons W, mu, A with A moving from 1 to 3 should all be massive, and the hypercharged boson U1 should be massless. But I concealed an important piece of information which you already have. The Higgs can have a hypercharge. If this number is exactly 0, then what I have just written here is exactly true. Okay? If this number is not 0 and has any value whatsoever, then this statement is not true, because there is mixing between SU2 and U1, because the Higgs transforms, I wrote down earlier for you the transformation of fields which are SU2 doublets and having a hypercharge. So the Higgs transforms simultaneously under SU2 and U1, and what it remains invariant under, what this wave remains invariant under, will be that combination of SU2 and U1 which keeps this wave invariant. Okay? Which in the case of the hypercharge being 0 would just be that U1, but as long as Y is not 0, then it's a combination of the hypercharge U1 and some U1 from inside SU2. Now the books all insist that the hypercharge of the Higgs is fixed to be 1. I don't believe this is a true statement. My opinion is that the hypercharge of the Higgs is not a physically meaningful quantity. It is to be absorbed in the coupling constant of the hypercharge U1, so you can call it 1, but no physics would change if you call it something else. I'll explain that. The only physical quantities are the ratios of the hypercharge of the fermions with the hypercharge of the Higgs. Okay, so let's implement this statement. So let's remind ourselves how phi 1 and phi 2. So I'll go on for about 10 minutes and we'll stop. That should be enough. So we've already written that these transform like this: alpha to A of x, sigma A by 2 e to the minus I g y, alpha y of x, y by 2 times phi 1 phi 2. Okay? And now we are trying to look for those transformations that leave the wave 0b invariant. So let's choose this to be 0b. And let's inspect these things to see which of them could possibly leave 0b invariant. Okay. Now, there are three sigmas, Pauli matrices. Of them, sigma 1 and sigma 2 are off diagonal, so they have no chance of leaving this wave invariant. Okay. So the first thing we should do is to here. Whatever leaves this invariant is going to be the unhiggsed part of the SU2 cross U1 gauge group. Okay, so we better take alpha 2 1 and alpha 2 2 and put them to 0. Okay, sorry about the notation. This 2 is for the gauge group, and this 1 and 2 are the first two components of this A, which has three components. Okay. Working with only the third component of this, and with that, we find that G2 alpha 2 third component times half times 1 0 0 minus 1 plus half gy times alpha y of x times y times 1 0 0 1 is the net value apart from the minus I of that exponent. Okay. Just rewritten that exponent without the minus I and putting in sigma 3, and here of course since there is no matrix, this is proportional to 1. So this whole thing is actually equal to a half. Okay, so this is easy enough. Now we see that if we can somehow make this component cancel between these two, then this whole matrix will be of the form something 0 0 0. When I exponentiate the matrix of that form, all powers of it will be of the same form, and it will never give me anything when it acts on 0b. So only the one part of this exponent will give me that, and that means it's invariant. Okay. So yes.
So y by 2 is a convention.
Yes, it's a convention. It varies in the book. Some people choose y and some people choose y by 2. And so make lower right component vanish tells us that we should take alpha y of x, the parameter. We should make a relation between alpha y and alpha 2, and the relation is precisely g2 upon gy. This is y phi, y of x. Alpha 2, 3 of x upon y phi, which obviously you can't do if y phi is 0. But which effectively means that in that case, the U1 hypercharge would continue to be a symmetry of the rest of the thing. So we've solved for the thing which leaves the Higgs wave unchanged. Okay. And now the question is, what generator? These are all related questions, but the question now is, what generator of SU2 cross U1 is unhinged? As usually people call it unbroken, which is basically seen from the fact that it's massless. Okay. And here the calculation is very simple. We first look at d mu. We look at d mu phi, either d mu phi. Okay. And we notice that plugging in the wave of the Higgs here and here, and putting in the gauge fields, the W mu plus minus, W mu 3 and K mu here and here, will give mass terms for the gauge fields. So this contains gauge field mass terms. And it's very easy to write down what it is. So I hope I've given you the prescription. Drop the small d mu, keep the gauge field. Drop the small d mu, keep the gauge field, and each of phi and phi dagger replaced by 0 and v. Okay. So the answer obviously will come out proportional to v squared. I will worry whether my Higgs wave is v 1 by r. That's that. Okay. So v squared by 8 times g2 squared w mu 1 squared plus w mu 2 squared plus g2 w mu 3 minus gy y phi d mu squared. It's a very simple calculation. I've given you the covariant derivatives on phi. Just plug them in and pull out only the terms that you want. The terms that are quadratic in gauge field, so these terms are all quadratic in the W's and V. Okay, and we find 3 terms. First thing is that we find 3 terms, therefore there are going to be 3 massive gauge fields, and therefore, as we fully expect, one linear combination of the SU2 and U1 remains massless, and that will be the one orthogonal to these 3 combinations. Okay. However, as I said, that mixing is true only if y phi is non-zero. Okay. Now it's important that gy is also non-zero. Okay, and in all these formulae, gy occurs along with y of phi. Okay, so we can actually choose y of phi to be any value we like and absorb that value into g. Okay, and so most people just decide that y phi is equal to 1. Maybe I made too much of this point. I'm just saying it's a convention in the sense whatever else it is could have been absorbed into the definition of g. Okay. But by choosing it to be 1, we are committing ourselves to a non-zero value, and a non-zero value leads to mixing. It means that a combination of W mu 3 and V mu has a particular mass, and some other combination which doesn't appear here, has no mass. And now we're almost finished. To understand those combinations, we write Z mu is equal to G2 W mu 3 minus Gy d mu. However, we keep room for a normalization because the kinetic term of these new gauge fields will not be conventionally normalized if I do this, and my physical consequences will be wrong unless I properly normalize it. The best way to understand how to normalize it is to first write the alternate or the orthogonal combination, which is Gy W mu 3 plus G2 d mu. Okay, it's clear that these two vectors in WB space are orthogonal to each other. Okay, and it's also clear that if I normalize both of them by the square root of Gy squared plus G2 squared, then this is actually orthonormal, which means the matrix 1 by square root Gy squared plus G2 squared, G2 minus Gy G2 is orthogonal. O transpose O is 1, and that's enough to be guaranteed that this is a legitimate change of variables from normalized fields to normalized fields. Good. Okay. So with this we read off two consequences and then we stop. Whoops, I think that I've not done exactly what I needed. So going back to this expression, we've now decided that Wi-Fi is 1, so that's not there. And we've also decided that this is not exactly Z. Z mu is this times this square root. And so this whole thing can be written as Gy squared plus G2 squared Z mu. And everything is inside a bracket with B squared over 8 outside. Okay. So these are our mass terms, and from this we read off the mass of W1 and mass of W2 is G2 times V by 2. So this mass depends on the amount of the Higgs wave, which by the way was so far an arbitrary parameter because it came from that lambda coupling constant we put as the mu, and we didn't say anything about how we chose those. But M of Z is different, and M of Z is actually Gy squared plus G2 squared square root times V by 2. Okay, so the mass of the Z differs from the mass of this by an extra Gy, and we see that it's strictly more massive than that. It's nice that we have really not done anything that can be called phenomenology, but we've already seen a true experimental fact coming out. Okay, we are still building up to the phenomenology. Now to close, I'll just rewrite this matrix in a nice way. So let's pick our favorite Nobel laureate, let's say Weinberg, and let's call G2 over this thing as cos of theta Weinberg. And then this is an appropriate way to parameterize any orthogonal 2 by 2 matrix, and theta W is called the Weinberg angle. I'm trying to remember who it was who claims that it stands for Glashow's weak angle. Salam maybe. Anyway, good, I think I got it right. cos theta should be G2 over the root and sin theta should be Gy over the root. Okay. So I hope that this fixes physical ideas quite well. Gy and G2 are our most important input parameters. They were the coupling constants of the hypercharge and the SU2 gauge group. And now we see that depending on some kind of angle in Gy G2 space, we have a single angle, Weinberg angle, which tells me the amount of mixing between SU2 and U1. Has the tape run out?
Almost 3 minutes.
Very good. I was almost run out. Good. I think from this point, so let me just write the last formula because it's pretty. So Z mu is cos theta W times W3 minus sin theta W times V mu, and A mu is sin theta W3. And A mu is massless. And here there is absolutely no ambiguity in this theory because it's massless and it's the only massless gauge field. It has to be identified with the photon. Okay. So I'll stop here. And next time, I think we've made good progress. So I think we can pretty much complete the standard model next time, which is what I've committed. So next time we'll complete this by talking about electric charge assignments, and we'll fix up all the hypercharges for everybody from experiment. And then we'll talk about mixing, mass matrix and mixing, and then